Hi, we are Team 30, Pand-AMMONIA. Today we'll be discussing our design and analysis of an ammonia production plant. My name is Benjamin Knepp. Today I'll be discussing the product and the feed stream associated with it. Alexandra will be discussing the process in which this product is made. Tyler will be discussing the economics of the process, including the sensitivity analysis and all rigorous analysis done to determine costs within the plant. Finally, we'll end with our recommendation for the plant, which at this point is to hold off until better market opportunities. It's crucial to many industries, particularly the farming industry. You can see that 85% of all ammonia produced goes towards fertilizer, with the remaining going towards nitric acid, polyamides, and other applications. The plant will produce ammonia from natural gas feed, containing about 90% methane, at about 40,000 pounds per year. Components of note here are hydrogen sulfide and mercury, which are both harmful to the process. Additionally, the rest of the feed contains several alkanes, water, nitrogen, and carbon dioxide. The plant produces 536 million pounds per year of ammonia, and ammonia is being sold at 17 cents per pound. The plant will be located in Philadelphia, Pennsylvania, with a capacity of 536 million pounds per year of ammonia. This exceeds our target production rate of 509 million pounds per year. I'll now hand it over to Alexandra, who will discuss the process by which we produce ammonia.
Hello, I'm Alexandra, and I will be going over the overall process used in a plant. Behind me you see the black flow diagram. It is divided into three different phases. Phase 1 is the purification phase, as well as the primary and secondary stream reforming. Next, we have the high temperature and the low temperature water gas shifts. And lastly, phase 3 is the ammonia synthesis, purification, and storage. Removal of mercury was priority number 1 when studying this process. Its desired role is to remove all traces of mercury in the stream because it is very poisonous to humans, catalysts, as well as it can damage equipment downstream. To do this, a mercury molecular sieve product was used. Next, we have the hydrogen sulfide removal. With the same thought process as the mercury removal, hydrogen sulfide is poisonous and needs to be removed before the whole process. To do this, desulfurization is used. According to literature, less than 1 part per million of sulfur is allowed. The process uses zinc oxide, a compound which reacts with the hydrogen sulfide from this feed stream and participates out zinc sulfide. Next, we go over to the primary stream reformer. The purpose of the primary stream reformer is to convert methane and steam into carbon monoxide and hydrogen using high operating temperature and low operating pressure. Below, right here, you see the main reactions that occur in the reactor. It is also assumed that the high order alkynes are in the gas are also reformed. Because this process is extremely endothermic with a temperature change of almost 2300 degrees Fahrenheit, the reactor was designed as a shell and tube reactor in order to amount for the large heat. Next, we go over to the secondary stream reformer. Water and methane then react with the carbon monoxide and hydrogen gas. So the overall goal is to produce more water to drive the steam reform forward and get as much methane converted into the hydrogen as possible. Next is the high temperature and low temperature water gas shift. The reactions both aim to convert carbon monoxide to carbon dioxide while generating more hydrogen used for the ammonia synthesis. The high temperature water gas shift occurs in a fixed bed reactor over an iron chromium oxide catalyst, while the low temperature gas shift also occurs in a fixed bed reactor over a copper zinc catalyst. And lastly, we go over the Haber-Bosch process, which is the ammonia synthesis, which converts hydrogen and nitrogen into the ammonia product. The process is done in a fixed bed reactor using a metal catalyst, under low temperature and high pressure. The ammonia is obtained in the bottoms product as a liquid at the purity of 99.72%. I will now hand it over to Tyler, who will go over the economics.
Hi, I'm Tyler, and just talk about the economic evaluation from our plant. So the total capital cost of our plant that we determined was roughly about $275 million. And from the start here, the OBL, which ends up being about 100 million of the 275, the IBL, which is about 76 million. Together, the OBL and IBL costs make up the total contrasting cost, which the miscellaneous cost comes from. And that's team cost, which is 8% of the total contracting, other costs, which is 4%, the pre-op and startup, which is about 7% of the total contracting cost, and then the catalyst data, which our assumptions that we made for the catalyst data was the life of the catalyst was 3 years, and since we're operating for 15 years, we took our catalyst price and multiplied it by 5, just assuming for the entire life of the plant. We also have our contingency price, which is about 45 million, and the escalation. The ongoing costs for the plant end up around $62.2 million per year. These costs include the utilities, which is seen as in purple at 42%, the raw materials, which is seen in blue at 26%, and the fixed costs, which is seen in green at about 30%. Also including the SG&A, which is about 2%. Within the fixed costs are the labor, the repairs and maintenance, the property tax, and the insurance. So for the labor, our assumptions are made that we have about 32 operators per day working for $80,000 a year, and we're having 3 shifts, so about 10 to 11 operators per shift, which may be a lowball estimate, but with a smaller plant like we've designed, it end up might being okay and save us a little bit of money. Here you can see the cumulative cash flow for our plant. As you can see, we're not making positive cash until about 2030, which is only with five years left in the lifetime of this design. The positive cash flow is a good thing, but by the time that we're actually making the money, it's not long enough of making money and to pay off the debts of the capital and the other expenses each year, which is seen here by the net present value graph, where we start our first year at negative $38, which is 15% of our $275 million capital, and then it never even reaches back to that point, and we're always at a negative net present value. Here is a summary of some of the costs from our plant and important data that we got from the cash flow equation. So we have the total capital cost, which we talked about earlier, which is $275 million. We have our yearly revenue from selling ammonia, which is about $91 million. The investor rate of return, or IRR, is negative 10%, which clearly would deter anybody from investing capital into the startup. And the required net back, which is what we would need to sell our ammonia product for to have a 15% after-tax rate of return, is about 24 cents per pound of ammonia, and we're only selling it for 17 cents per pound of ammonia. And now Cole is going to talk about some of the economic sensitivities and wrap up with recommendations and conclusion.
Hi, I'm Coach Williger, and I'll be talking about the sensitivity analysis and the overall recommendation and conclusion for the plant that we designed. So our first sensitivity analysis that we did was we looked at the NH3 ammonia cost as a market through time, and then we decided what if this market were to change, or is it going to change, and then how much money could we possibly make from our product if it were to move around a little bit. So what we did to start with this was we looked back at NH3 costs through time, and as you can see, the graph that shows here is the price of ammonia, and the big jump that you see up in it is what we assumed to be the 2008 recession, where the cost just skyrocketed. But apart from that, you can see how it's pretty steady, and then after the recession, it steadies back down again. So we basically determined from this that NH3 is a rather non-volatile market. It's stays rather constant of where it's at, and what we have from ours is basically right where the flat part is, and that's 17 cents per pound of ammonia, or $300 a ton. But the one thing that we wanted to look at was if it were to jump up just a little bit, so from 17 cents to say 20 cents. And so that's all we did was looked at that, and that is what this chart here summarizes. And basically, if it jumps up just a few cents per pound, our net present value goes from way negative 55 million basically, all the way up to 15 million here. And also the after-tax rate of return is at 5%. It'll jump the whole way up to 10%, which still isn't at the 15% that we wanted, but it will get us closer to that objective. And then the investor's rate of return goes from a negative to a positive, which may draw some investors in so we can get some money for capital, but still at a 2% investor rate of return, it would be hard to get any investors to invest in our project. The next thing that we looked at was trying to adjust our fixed costs, which is actually very hard. So what we looked at for this was, what if we could cut our workers down, say from 32 workers to 20 workers, and then how would that adjust things? And also we looked at cutting tax rates. So if we could cut tax rates and workers down, how much would this make our plant more profitable? And so for this one, we end up getting that our total fixed costs can be cut lower than half if we did this, but it's quite unrealistic, I guess, to determine that our tax rates are going to be cut cheaper. That just wouldn't happen, I guess. Okay, and then our next part was we looked at, well, what if we decided to draw this project out longer, slowly build the plant instead of building it all at once, so maybe let the market develop a little bit. So for our base case, it's going to be built in 3 years. We spend all of our capital money, and then we start producing. And as it is right now, we're making negative profit until maybe 15 years down the road. But what we did for this case was maybe draw the capital spending in the building, site development, everything, draw that out for 5 years, and then see where we go from there. Doing this does cut the capital cost down some, but you still end up making no money basically. We're still making the same amount of profit off of our product. But so this sensitivity analysis was another bust basically. Our last sensitivity analysis was looking at some of the capital costs that we could cut to hopefully make a profit in the end. And this one was actually quite promising. So what we tried to do for this one was, right now our capital sits at $275 million to build the plant, but we wanted to cut it down to say 200. And where we looked at doing that was taking our wastewater streams and maybe trying to purify out some product from that and then selling it to make some more money. And the main part we looked at that was out of our pressure swing absorber, we had 105,000 pounds per hour of wastewater coming out with a lot of CO2 in it. So what we thought we could do for there is, if we take out a bunch of that CO2, you end up having about cut our wastewater stream in half, and then purify the CO2 and hopefully sell it. And that was the one thing, the big one that we looked at. And then our environmental costs actually go down by a very big amount. And we determined we could make about $4 million if we could purify all the CO2 we got out. So our capital costs went down, but we made a lot more money. And doing that, it set our net present value from negative 55 million to positive 5 million after 15 years. So doing this could eventually help, in the end, actually having a positive net profit plant. Okay, so for the conclusions, at the current state that our plant is built in, we recommend that we do not continue building or start building anything, but there are a few things that we could do. And one of the things we could do is maybe shelve the project and just let it sit there for a while. Don't actually start building anything. Let the market develop. Maybe the price of NH3 will go up a little bit, and you can sell your product for a little more. And like we talked about earlier, all we need is basically a 3-cent increase per pound of product, and we could make some money off of it. Or perhaps with the Marcellus shale booming and everything right now, our feed natural gas costs could decrease a lot to the point where we could purchase it for cheaper, and then eventually you could make some money in the end.